abstract terms, what you generally see is that if you plot the efficiency against the number of processors, that if you increase the number of processors, then the efficiency goes down. Vice versa, if you plot the efficiency against the workload, yes?
But this plot does assume that if you have more processors, you will use them in some way. Even if they're idling, they're still consuming
Sure.
power.
Yeah, you have to take that into account.
Because if that's not the case, I don't see why the efficiency would.
No, but then P means in use, right? If we would plot the efficiency against the workload and the number of processors remains constant, then if the problem size goes up, then also the efficiency goes up. So somewhere in the middle, there must be a means to have that the efficiency remains constant. Well, first of course, the problem is, what is problem size? Well, one choice would be the input of the problem as a parameter for the size, but that's not a very handy choice because the interpretation of input size changes from problem to problem. For instance, if we have matrix addition, then if we enlarge the input size by a factor of 2, we have 4 times the execution speed of the algorithm. In this case, a better definition would have been this bar should be here, because it's related to this example, that doubling the size means doubling the amount of computations. So having the input size as a parameter is not very handy. So what we use is the problem size, Wn, which is equal to the number of basic computational steps in the best sequential algorithm, which for the matrix addition is order n squared. In that case, if we equal the number of steps to problem size, then we can also equal the sequential execution time to workload, right? So we change dimensions, right? We have unit steps or number of calculations instead of seconds and time. I mean, that's equivalent in this case. And the reasoning with this formula is way easier in terms of ISO efficiency than talking about real time. Now, how do we calculate the cost optimality of a parallel algorithm? Well, the recipe is given here. Given is the problem size parameter, n, and the workload in terms of the number of basic calculation steps of the sequential algorithm, which is generally a function of n. Fn. Now we have to determine the parallel execution time, which is parameterized by P and n, of course, and show that it holds true that the cost, which is equal to the definition here, P times the parallel execution time, is in the order Fn, right? The workload. Now sometimes you have to impose a condition, for example, that n is lower bounded by another function of the number of processes to get rid of the variable p in such a way that only that the highest term of n in C is preserved. That's the general recipe you have to follow to calculate the cost optimality of an algorithm. An example. In the first one is just an arbitrary example. Given is the sequential execution time in terms of the workload, which is n. execution time is n log n divided by p plus p. Right? Then we calculate the cost, which is n log n plus p squared. Right? Now you can immediately see this is not order n. Right? So this can never be cost optimal because there's an n log n term which you can never get rid of. Second example. The workload is n squared. And the parallel execution time is n squared divided by 2p plus n times p squared divided by 10. Right? The same, you determine the cost and you get this expression. Right? Now here you see that we have to equal it to the workload of the sequential algorithm, which is n squared. So this is fine, and this is not fine. So we have to impose a condition on this one to make it n squared. And we can do that by assuming that n is lower bounded by p to the power 3. And then we replace this term by n, and then we have another n squared term, and then the order is also n squared. Right? So we impose the relation between n and p in this way to achieve cost optimality. Third example, likewise, here it's given that sequential time is n log n, the parallel execution time is n times the square root of n. Here you end up with p times n times square root of n, which supposedly should be n log n, but this is never the case. So this is not constant. Right? So 3 examples following the recipe to determine cost optimality. Okay. Some generalities about isoefficiency function. We have this, replacing Ts by W here, and speed up replacing Ts by W. Right? These two formulas. If we substitute T here, this one in this one, right? We solve Tp out of this equation and substitute it here, we get this equation. And if we divide by W, then we get 1 over, the efficiency is 1 over 1 plus T overhead divided by the workload. Now, if you look at this one, you can see that efficiency is fixed if this term is fixed. Right? If this term remains constant, then the efficiency is constant. Right? So the relation between the overhead and the workload is crucial in determining whether you can achieve an isoefficiency relation. If we rewrite the previous expression, this one, by solving W out of it, right? We get this expression. W is equal to efficiency divided 1 over the efficiency, 1 minus the efficiency times the overhead. Now, if we require a constant efficiency, this is a constant. And that means that W is a constant times the overhead function. And this equation function is called the iso-efficiency function. Right? Okay. So, put it in the board. It's a constant times the overhead. Right. Go back to our example, what this means. N numbers on P processors in an optimal way. This we already derived before. These expressions, that the overhead in this case was given by this minus W, and there again I substitute N instead of N minus 1 to make the equation a little bit more simple. And it turns here that the overhead is equal to P log P. So our function here boils down to W is K times 2P log P. Which means that if, because this is a constant, that the workload in the is in the order of P log P. Meaning that if we want to enlarge the number of processors from P to P prime, we have to enlarge the workload with this factor to keep the same efficiency. Right? Now we might have more complex functions as the overhead function. What do we do then, right? Suppose we have this overhead function, which is a kind of, well, what we can do then is see whether which of these individual terms is the most dominant one. Let's first look at this one, right? Then we see that we have this equation, that the workload here is proportional to P to the power 1.5. And if we look at the other one, we see that the workload is equal to this term, and then we solve W, and we see it's equal to K to the 4th, but it's still a constant, times P to the power 3. Well, here we can really get rid of this term because it's way lower than this term. So this is the only one we have to take into account for the iso-efficiency function in our scalability analysis. Right? So here we have that W should be in the order of P to the power 3, because otherwise we cannot achieve any scalability of our system. Now, that's all fine, but is iso-efficiency also cost optimal? Because we might have arrived at an iso-efficiency number at the cost of an unrealistic amount of processors, and then we're far from our goal. Well, let's go to a number of very simple manipulations to see where we stand. This is just the definition of cost optimality, right? Efficiency is in the order 1. Then we replace efficiency by its definition. S over P is must be then order 1. If we move this to the other side, we see that this speedup must be in the order of P. We replace this one with the original definition, meaning that the sequential execution time is equal to the parallel execution time times order P. This is equal to the workload, in this expression, right? combine these two? No. We remove the order because of this, the definition of the order symbol. We may also rewrite this expression to this expression, to moving it to the other side, right? So P times TP is in the order of the workload. Then we replace this one with this definition here. We write out what the order symbol means here, and then conclude that the overhead function must be smaller than a new constant times the workload. Meaning that the overhead must be upper bounded by the workload, or the workload be lower bounded by the overhead function. Which you kind of originally could also see by looking at the original expression. Now we originally said that if this one is constant, right, then the efficiency is order 1, it's constant. But if we take this expression that the workload is lower bounded by the overhead function, we kind of have the same result. Right? And we only say that it's equal or better than that. So in order to do that, to achieve cost optimality and ISO efficiency, we require that the workload is lower bounded by the overhead function. It must always at least grow equal or faster than the overhead function. So this is just an algebraic trick. So cost optimality is guaranteed if, in other words, if the overhead doesn't grow faster than the workload. Kind of intuitive, right? I mean, also look to these formulas a bit in the intuitive way, right? Not only the formulas. Right, again, an example, adding n numbers p processors. We already derived this expression, that the cost here is n plus p log p, should be in the order of n, and that only holds if n is lower bounded by p log p. The workload is n, so the workload is lower bounded by p log p, right, to derive cost optimality. Well, this is an argument if there is a lower bound on the ISO efficiency function, but I leave it to you. The answer is that the ISO efficiency function is lower bounded by p, and the argument is that if we add more processors but the workload doesn't grow, then in the end the workload would grow slower than the order of p, and then p would eventually exceed w, leading to a drop in efficiency, which is kind of logical. Right? So this is a bit of a theoretical argument. Right. Another notion is the minimal execution time. Is there any relation between the optimality things and the minimal execution time? Because that's what we are after, right? We're doing parallelism because we want a low execution time. Well, suppose we have our example here, and we plot the parallel execution time against the number of processors for n is 32. We get this curve. Right? Now, how do we derive the minimum execution time? By looking at the figure, but that was not my question. general, I mean it's take the derivative of the parallel execution against P. Right? So take the derivative of TP against TP and equal it to 0, right? That you all learn at high school to do that. Okay, let's take our example of adding n numbers on P processors. We had the parallel execution time is n over P plus T2P log P using our model, right? If we do that, then the minimum, and when we take the derivative, right, and equal it to 0, it follows that the minimum execution time is achieved at point n divided by 2. And that the minimum execution time itself is 2 log n. Is exactly this point. Now, looking at this graph, would you consider this an efficient solution?
Well, you can almost get the same execution time by using half the processors.
Right. If I would choose, say, halfway the number of processes, I hardly lose anything, right? So all the processors I've added here is basically a bit wasted. So the minimum execution time is no guarantee for any efficiency. Now the question is, would cost efficiency yield get us to that point, right? So combining the notion of cost efficiency with minimum execution time, if that would lead to a point somewhere here, giving us a kind of the balance between minimality and efficiency. Here you can also see that this execution time is not cost optimal, right? Because the cost of this minimum execution time is n log n, and it should be order n. So it's not cost optimal. It's easy to show that if you take this one, it's definitely not cost optimal. So minimal cost optimal execution time. Now, we just said that cost optimality requires this, right? That the workload is low bounded by the overhead. Now, suppose the overhead function is given by this function f, which is a function of p, then substituting this one yields this one, and if we solve p out of it, then it's upper bounded by the inverse of this function with the workload as parameter. And if we substitute this p in the cost optimal in this function, in the parallel execution time, we would get this formula. Well, that sounds very abstract, right? Let's see how this works in practice on an example. Well, we go back to the example of adding n numbers to P processors. We have derived that the parallel processing, the parallel execution time is n over P plus 2 log P, and that the ISO efficiency condition is n is lower bounded by P log P. That's our starting point. But what we have to do is getting rid of this P in the expression, right? Because otherwise we're going nowhere. So what are we going to do? Well, let's start at the lowest point, that n is equal to P log P. We log both sides of the equality, so this one becomes log n, and this one becomes log P log P. Right, we can do that. Which is equal to log n is log P plus log P. This is a very small term, so we can say that log n is approximately log b. Therefore, if we look at this one, we may replace this one by n is p log n, right? Substituting this one in this log p term, we have this back. Or if we take the inverse function, p is equal to n divided by log n. Okay, there we have our p expressed only in n. We substitute this one back here in this piece, right, and derive a function in n, which in the end turns out to be 2 log n minus log n. Right? Now, if we do use that one, right, we see that the point we have chosen is here, right? And for every point in this shaded curve holds that it's cost optimal, and beyond it point it's not cost optimal anymore. Which is also kind of intuitive. Eh? If you look at the figure, it's kind of what you see. So the cost optimal point is 6.4, but we don't have 6.4 processors, of course. We have to choose the closest one in the safe region. So for 1 over p between 1 to 6, there's the solution is cost optimal. Right? Okay, now how do we do this? This was the minimal execution. Now, how do we do this in a template for a generic example? We calculate the parallel processing time. We determine the ISO efficiency condition in the second step. And we solve P out of the ISO efficiency condition to obtain the cost optimal region. Right? That's the general scheme. Well, just another example along the line given, right? Suppose that the sequential execution time is n squared and that the parallel execution time is given by this expression. We've already seen this, then the cost is this expression, which should be equal to order n squared, and that's only true if n is lower bounded by the p to the power 3. Right? And by solving this, by solving this one out of this equation and substituting it back, we can derive the optimal number of processors. Right? And the minimal execution time is this, right? P is 5.4, so P minimal should be here. And the cost optimality region is given by 1 smaller than p smaller or equal than the third power root of n, right? Which is approximately here. So here it's somewhat closer together by virtue of this function. Right? So it's not that difficult, right? So the idea is to have this condition, this ISO efficiency condition, and then say something about the relation between P and N, the growth relation between P and N. That's the idea. Right. What's this? Of course, we have to choose. If we want to select algorithms, we have to. What we see here is that for a specific problem, we can have different algorithmic variants, right? And they all have different characteristics. For instance, this algorithm A1 has a parallel execution time of 1. But for A2 it's n, and for A3 it's square root of n, and for A4 it's so it's a bit dependent on what we optimize for, right? So if we optimize for speed, then algorithm A1 is the fastest because it's one step. Right? If we optimize for efficiency, then A2 and A4 are good candidates. If we focus on cost optimality, then A2 and A4 are suitable candidates. Right? So it doesn't mean that given an algorithm, you always select the right algorithm. There are other metrics, and I skipped this one because it's a bit of a side. This one I think I already discussed with you, the serial fraction model, where you split the workload in a serial part and in a parallel part. Right? I started the course with giving this example, I think. And then alpha is, which is defined as the serial execution time divided by the workload, is called the serial fraction. And if you manipulate this function, you get these speedup formulas, and that is the basis for Amdahl's law, where you derive that the speedup is bounded by 1 over the serial fraction, right? Which is the same. This is a different way of looking at a Formels model, but also works. Right. Good time to stop, I think. So I've shown you a number of notions and a number of recipes. If you remember these, especially for the exam, right? Keep them in your head, good in your head. Then the solution to the problems that are in the exam should be posed not really that much of a difficulty, I guess, in a systematic way. Okay, next time we're going to turn into